Well, that was mostly my introduction. Except to point out that these days you're ICL Professor of Computer Science at Manchester University, so you've transcended your Cambridge roots, and it's gone to the other birthplace of computing, haven't you?
That's right, yeah.
Yes, so your career has continued after Acorn and ARM in rather a prestigious and successful way. Mm-hmm. You didn't all stop when you stopped working with Herman.
No, I think of course ICL was the combination of the British computer industry in the 20th century. And yes. Until it was taken over by Fujitsu in the 1990s. Yes. And I think there are two vestiges of ICL still left. One is my chair and the other is a pension fund.
Which says everything about the state of the disunited kingdom today. I promise that's my last bad Brexit joke. So my name's Bill Thompson. You may know me from such well-known instructional videos as How the Internet Works and What is this thing called the World Wide Web at The Guardian, and I'm a journalist, a hack and a pundit is how I choose to describe myself. But also, crucially, I'm a Cambridge computer person. I did the diploma, and like everyone who's ever studied computer science at Cambridge, I discovered that there was, sitting in Acorn Computers, a job for me when I chose to turn up and take it. In my case, I applied for a job working in the language processing, language intelligence unit, the Esprit project, was turned down, and Mike Chalice spotted my CV on someone's desk, phoned me up and says, come and work for us. I don't believe there was anything as formal as an interview in those days. It would have been irrelevant, apparently. And so in the mid-80s, I worked at Acorn for a number of years, around the time the ARM was moving from the fab and the lab into production. And I think the reason I was invited to talk to Steve today is because we're old friends and many of my old friends and colleagues are here, and because I was scarred by the same sorts of experiences and can therefore bring a certain sort of whatever genuine emotion to the Q&A session about those days. So we heard from Herman there that you were in fact a mathematician, and you were somehow corrupted to move into first aeronautics and then computer sciences, away from the purity of numbers. How did that happen to you? Where did it all go wrong?
I was a mathematician as an undergraduate, but my interest very much lent towards the applied side. So I was never a pure mathematician. I've never been pure. My interest from my teenage years was aeronautics. I was an aero modeler in my teens, not a very successful one. I continued that for some years afterwards. So my maths lent towards fluid dynamics, and there was a fairly obvious opening in engineering to take that fluid dynamics across into a more practical domain. And in the course of doing aerodynamics, I got involved in the processor group, as Herman described, started building computers, started using them in my aerodynamics experiments.
So what sort of computers were you building? Because you were doing a PhD, and then a Rolls-Royce research fellow at EMMA. So you were working with what at the time? What were the machines you were building?
The official computer in the lab that I was using was a Computer Automation LSI-4, I think, which was a box about this big with a 16-bit something in it. Yeah. But I was building things on the side for fun. Firstly, this 2650 system, and the university processor group, we used to go round and sort of admire each other's bits of kit and break them. And I remember one of Sophie's first comments on playing with my 2650 in my front room was, "The memory's broken." I found a bug. Yes. And life with Sophie continued pretty much like that for the next decade. Right. So I was using computers. I got involved in the university processor group when Herman approached me along the lines he described and said, "We're thinking of starting this consultancy. Are you interested?" And I said, "Well, for me it's just a hobby, but if you think I can help, then I'm happy to give it a go." And I think there was some initial meeting in the Fort St. George on Midsummer Common where Herman and Chris Curry and Chris Turner and I met. I have no idea what we talked about, but things moved forward from there.
Right. So you were then a research fellow. You weren't actually working. Was this before Acorn Computers existed as an entity?
Yes, the entity that emerged after these discussions was actually called Cambridge Processor Unit Limited, or CPU Limited, which must have taken a lot of imagination, right, to come up with a name like that.
Yes. It's the vision that we
exactly, yes. And we were building things, and one of the earliest things I did was actually hand prototype an MK14 system.
Right.
That Science of Cambridge was producing, which was sort of Chris Curry's spin-off from the Sinclair organisation.
Right.
And I remember Sophie came in, looked at the MK14 and said, I can do better than that. Went home and over Easter came in with a prototype based on the 6502,
Right.
which Herman and Chris looked at and decided they could sell as a product, and that became the Acorn System 1.
So you were working on the MK14. You were, but not actually an employee at that time. So you're part of that sort of loose accretion of interested people around the team.
I was very much still a hobbyist, effectively, but with the connection in to CPU Limited. I was initially a research student funded by the SERC at that time, which did not allow me to undertake additional employment. So the kind of deal was that CPU gave me interesting bits to play with, and I gave them bits of design back.
Right.
So it was a kind of in-kind
And
deal.
you were happy with that exploitation at the time?
Yes, yes. It was good fun.
And then when did things formalise them? Was this before or after the deal with the BBC that resulted in what was going to be the Proton becoming the BBC Micro? What was the timeline there for you?
The difficulty with answering that question is there are so many people in the room who know this story that I'm bound to get something wrong and get into trouble. But
Okay, anybody who has a correction, put your hand in the air and keep it there, and we'll come to you at the end.
But I think the timeline roughly was that Acorn had developed the Atom as a product. I was not involved directly in the design of the Atom. That was largely managed by Chris Curry and Nick Toop, I think. And of course, Sophie wrote the basic that was on the Atom. But the company was talking about what they would do to build on the success of the Atom. And we were sketching things on bits of paper, and I was involved in the architectural design. And the thing we were sketching was a thing that we called the Proton, as an internal code name, I think, rather than an agreed product name at the time. But we could see the world was already beginning to move on from 8-bit. 16-bit microprocessors were appearing. And so the Proton was sketched out as a dual processor with a 6502 front end doing all the I/O and probably some sort of 16-bit back end. And we had this sketch, very rough sketch on a piece of paper. And then when Chris Curry picked up that the BBC was going around looking for suitable potential machines for their program, we looked at their requirements, which we were a very long way from meeting. I think the requirement was a Z80 running CPM, and we had a 6502 running something homebrewed.
Yep.
But we decided that the way to take this sketch design and move it closest to their requirement was to sort of kind of leave the second processor as an option and present them with the front-end 6502 machine as the basis for the BBC Micro.
And that became the machine that was projected to sell a few tens of thousands of units and sold, 1.5 million in its life?
I believe the original estimate was 12,000.
Okay. Right.
Only out by 2 orders of magnitude.
So unlike today's BBC. Okay, just let's say that. So unlike today's BBC. And you were then working, you got your doctorate, you were on the payroll, were part of that team.
At the time that we got the BBC contract, I was not on the payroll. I was in the last year of I was a Rolls-Royce Research Fellow at Emmanuel College.
Right.
But that 3-year fellowship was coming to an end. And the BBC contract clearly created an interesting opportunity. So at the end of the fellowship, I joined Acorn on the payroll in October '81.
Right. And how many people in the room were working with Acorn around then? Anyone? Okay. Yeah. I hope you weren't. You must have been around.
Maybe
20, 30.
Right.
Yes.
Yeah.
And we,
some of you are
we
here.
were still...
We were fitted into 4A Market Hill, didn't we? So you can't,
Yes. I walked past...
can't have been more than 20.
I walked past the entrance to 4A Market Hill. It looked as dingy and unattractive as I remember it.
I believe it's preserved as a historic monument. I mean, some of those cans of beer have been there for 30 years.
Well, the pigeons have.
Yes, yes. Once they die, they just sort of stay there.
Yeah, that's right, yeah.
Now, we all know that obviously from the 6502 chip in the BBCB, you went on to design, Sophie, the ARM chip. What is surprising looking back into history is how quickly that happened. That it wasn't like there was a decade of success and then you thought, well, let's do something next. It was almost as soon as these machines were coming out of the door, you were thinking about what happened next. Was that what was it like for you then? Was that the process?
Well, the BBC Micro was a real runaway success. I mean, nobody anticipated the kind of wave of popular enthusiasm that it would engender. One story I remember is that we were asked to give a seminar on the BBC Micro quite early on at the IET in Savoy Place. Then it was the IEE. And we turned up, Chris Turner, I think Sophie and I went along to give this seminar, and they had a big lecture theatre with a capacity of 600, but 3 times that number turned up. People had hired coaches from Birmingham to come to this seminar on this machine.
Wow.
And they had to be sent away because, even then, health and safety didn't allow you to put 2,000 people in a 600-seat room. So that's just one anecdote that sort of underlines just how much excitement the machine generated. And of course, it didn't generate just excitement. I believe it also generated some revenue.
Yes.
That put Acorn in quite a strong position. And so, of course, we had to think about what would follow on. How could we build on this success? What should the next machine look like? And most of the world was transitioning to 16-bit microprocessors.
Well, you said the design of the Micro came from a design that was supposed to support 16-bit right from the start, so you had already been anticipating that.
Yes.
And you cut it down to deliver something that would meet the BBC's requirements.
And indeed, we did bolt second processors on.
Yes.
So we did eventually deliver the BBC's original requirement through a Z80 second processor running CPM.
Yeah, I remember it.
But we also added the 32016 in the Cambridge Scientific Workstation.
Yes.
We added 6502 second processors, which gave you the same basic instruction set, but more memory and more speed.
Yeah.
So we did extend the machine
Yeah.
through the second processor port, which was mysteriously called the tube.
Yes. Mysteriously?
I have no idea why it's called it. I mean, the tube persists to this day, embedded in bits of ARM code here and there, because it provides a kind of logical interface. But
Yes.
I can't remember where the name came from.
I'm assuming it was the bus and the tube, that it was a bad joke by an engineer. But that's an assumption.
That's a reasonable guess.
Knowing some of those engineers and their sense of humour, I'd say assume the worst possible joke.
But I don't think we were that London-centric, actually.
Ah, right, okay. Yeah, otherwise, it could have been called the punt, I suppose. Too slow for your needs. And we're going to come on to that shortly.
Yes.
About things speeding up. So you have this remarkable success, you have some funds, you're using a 6502 processor, which does the job. What possessed Acorn to think that the sensible option was not to go out to a very large US-based fabricator of chips and buy their high-end chip with all the money you've got, but to build your own? What form of insanity is this, or hubris?
It was, in retrospect, a very strange decision. But we had played with these 16-bit micros, and we'd used them in product, but we didn't like them. Okay, and this is going to get technical. That's a warning. We didn't like them for 2 reasons. The first reason is they had very poor real-time performance. In other words, on the BBC Micro, we made things very simple and efficient by working the 6502's interrupt system very hard.
Yep.
The 16-bit micros had much worse interrupt response.
Okay.
The thing I remember about the 32016 is it had a memory multiply instruction which took 360 clock cycles to complete. during which it was not interruptible.
Whoa.
Now, its clock was only 6 megahertz, so that was 60 microseconds.
Yeah.
And a standard density floppy disk produces a byte every 64 microseconds, double density every 32.
Okay.
Now, you could do that easily with a 6502,
Yeah.
but you couldn't do it. So real-time response was one of our bugbears. The second bugbear was probably even more fundamental, was we'd formed the opinion that the thing that determines the performance of a computer more than anything else is the processor's ability to access memory bandwidth. Okay? And standard memory, commodity memory, was dynamic random access memory, DRAM.
Yep.
And none of these 16-bit processors could use the bandwidth that was available. In other words, they wasted the most valuable resource in the machine.
So they were just sitting there processing, and they could not move stuff to and from memory as fast as the chips would allow.
As fast as the memory would support, yes. They basically did not efficiently exploit the most valuable, and this is the most expensive resource in the machine. The most costly component is the memory.
Okay.
And if you don't fully use it, you're being wasteful.
Right. Well, as a programmer, it was at the time all about how much can you squeeze into as little memory as possible. And you're saying you're then wasting your access to...
Yes, but it's not the amount of code, it's the rate at which you can access it and move data.
Yeah.
And we were sort of scratching our heads thinking, don't like this, don't like that. Really don't like that one from Intel. And I'm not quite sure which route it came through, but somebody, I think it was Andy Hopper, it might have been Herman, dropped some papers from Berkeley about the Berkeley RISC 1 and 2 designs.
Okay. So these are the reduced instruction set computing.
Yeah. So RISC here does not mean danger. It's RISC with a C. It means reduced instruction set computer. And this was a kind of paradigm shift in computer architecture against the trend of the late 70s, early 80s of moving microprocessors more towards mini computer instruction sets with lots of very complex things, where the trendy phrase at the time was closing the semantic gap between the architecture and the high-level language. Okay?
Right.
Moving the instruction set up so it could do things like subroutine calls as single instructions. And RISC was the antithesis of that approach. RISC was strip your processor instruction set right back to the simple essentials, let the compiler do all the hard work of using that, and use your transistor resource on the chip for something which delivers more performance than these high-level instructions.
And this was motivated by performance considerations primarily. It wasn't just a theoretical framework, it was how do we get more out of the transistor arrays that we can build at the time.
Yes, you have a finite transistor resource, and what's the best way to use it is the issue. Okay. So there was this idea of the push towards simplicity, which was attractive. Even more appealing was the fact that the RISC-1 had been designed by a postgrad class in a year, so a bunch of students had spent a year designing this and produced a processor that was competitive with the best that industry could come up with.
Right. So there was working silicon out there that demonstrated these principles work.
Yeah.
Okay.
So we thought, that looks smart. Let's have a go.
Right.
Now, when we thought, let's have a go, our expectation was that this was such an obvious good idea that the industry would obviously pick it up, right?
Yep.
Industries shouldn't miss an idea that's this obvious. And we get trampled underfoot because the resources that the likes of Intel or National Semi could bring to bear would just sort of, rush ahead. But in the process of setting off on this path, we'd learn a lot. And then when something interesting came on the market, we'd be much better informed to know what to buy.
So it was, just to paraphrase that, so it was much a research initiative within Acorn to say, let's find out how this stuff works, so that when something does come to market, we will be able to assess and evaluate it and choose the best one for ourselves.
Yeah.
And that went wrong.
Yes, it didn't work out like that. The other sort of slightly strange situation that Acorn had got itself into was that Herman and Andy Hopper, between them, had persuaded themselves that Acorn should invest in silicon design tools and people. So we bought workstations. I think the Herman quote of the day was, in the future there'll only be two sorts of computer companies, those that have learned to design on silicon and those that have gone out of business. Right? and so the plan was Acorn will be in the first category. Yes. So
sounds reasonable.
We trawled the world. I think Andy Hopper in particular had steered us towards tools from VLSI Technology. Yes. Apollo workstations, which were 50,000, 60,000 pound boxes with you know, no compute power in at all.
Great
And
screens, though, I seem to recall.
big screens,
Yeah,
yes,
yeah.
big monochrome screens, I think initially. And Acorn had then recruited some experienced chip designers. So there was a team that was led by Robert Heaton. When did you join, John? It was mid-80s, so it was later than that. So yes, I sort of slightly, Jamie Urquhart I think joined early,
Oh, right.
Dave Howard,
Okay.
Harry Oldham. Jim Sutton was in there, yeah. So they got these chip designers who basically didn't have any chips to design.
Okay.
So Sophie and I had, Sophie had designed an instruction set. I'd developed a microarchitecture, ideas not fully developed, and we had chip designers looking for some chips to design. So we put this together, and 18 months later we had the first ARM Silicon on 26th of April 1985.
26th of April 1985.
That was the date, yes, and three.
Local time?
John, it's
BST, thank you.
it's actually written on the champagne bottle you can see outside. The 3 o'clock is when it started running programs,
Right, okay.
and Herman cracked the champagne, and something was written on it. And so we did it fairly quickly. We did it very simply because none of us had designed a microprocessor before. I mean, our chip design experience was fairly minimal. So we really did keep it as simple as possible, we thought.
And what does simplicity mean when it comes to that process design? Is it about clean interfaces and sort of identifying, you know, sort of the logical units on the chip so that it works, it can be looked at simply by someone who does not understand chip design and they can see how it works? What are the principles of simplicity you're bringing to bear here?
Okay, so in what way is ARM simple? Well, it's simple, firstly, in terms of its transistor count.
Yeah.
So it used relatively few transistors, about 25,000 in the case of the first processor, which was very small compared to the 16-bit processors we were competing with at the time. But also, there's also a lot of regularity. Okay, so transistor count isn't a pure measure.
No.
So it had following the RISC tradition, it had a fairly large register file, and when you design one bit of a register, you can then design all the others by cut and paste.
Okay.
So you get quite a lot of transistors for a small amount of effort.
Yeah.
One fairly brave decision we took fairly early on, sorry, this is going to get technical again, was to use double metal CMOS. In other words, we'd have 2 metal layers on the chip instead of the usual 1.
Right. What does that give you?
That allows you to partition the design into independently constructible chunks,
Okay.
which can then be connected together very easily.
Right.
Whereas if you only have single metal, you basically have to start by designing the entire power grid, because
Okay.
you can't cross power and ground over anywhere if there's only one metal.
Right.
So you have to design the whole grid and then fit everything in.
Okay.
Whereas the 2 metal approach gave us more flexibility and more modularity in the design.
We say it was a brave design decision because it wasn't the way experienced chip designers would have done it at this stage.
Well, second metal was just coming in.
Okay, so
And it was flaky, and we did get bitten at one point but not on the ARM chip, on the memory controller chip.
oh right,
We had a metal 2 problem,
Okay.
but in manufacture.
right.
So it was,
Yeah.
it was pushing the edge a bit, but to make the design easier to construct and assemble.
And at this stage, had Acorn as a company committed to the ARM chip as being the basis of a product line, if a second processor or something, or was this still, we're learning how this goes, we expect someone else to come into this market and we'll probably end up using their stuff? You know, how was it psychologically then?
I think by the time we had the working silicon in our hands, which surprised us as much as anybody else, I think we were fairly clear that this was something we could build product around. I mean, initially it was second processors, but the ARM was always designed as one of 4 chips. So there's a 4 chip set. The processor itself, the memory controller, the I/O controller, and the video controller.
Yeah.
And Mike there was the design lead on the I/O controller. Tudor Brown was design lead on the video controller. I was lead on the processor and the memory controller.
Right.
And the VLSI group led by Robert Heaton did all the back end design and implementation of all 4 chips.
Right.
And we had this machine in mind. Now, it took some years to get all the chips together. We did them in series, and that's why the Archimedes didn't appear until '87, which was the first machine to have the full chipset in it.
Yeah.
Before then, we had the second processors, which were based just on the ARM itself and a bunch of memory.
I remember getting an ARM second processor on my desk in the Silver Building when I was working with Mike Chalice in the engineering department. So, and that was a great moment, you know. And then, you know, we all got to play Zarch and sort of waste all of our time.
Absolutely, yes.
That's it was the obvious thing to do. And then the Archimedes arriving. And as you say, that was the point at which, so Acorn is now moving to basing its product line around the RISC chips.
Yeah.
The next big step, I suppose, was the decision to float off ARM with VLSI and Apple and into a separate business. Were you involved in that process, Dan?
I was not directly involved in the successful part of that process because I left Acorn at the end of July 1990. I moved to Manchester.
Yeah.
I had spent some of my time in my last 2 years there looking at ways one might set up a company because ARM's business was basically UK education and a few other bits. And so ARM's budget was determined by government decision.
Yeah.
And that budget was not sufficient really to support the kind of investment that was required to keep the processor at state of the art.
Right.
So we looked at various plans for separating the company out, and none of these worked. Okay. We had a series of unsuccessful plans, and they didn't work because the basic thinking was the business was based on royalties, and royalties for a small part of a chip. You'd have to sell millions.
And who's going to do that?
And I mean, you know, this was inconceivable that you'd sell millions and make the budget balance. So none of these plans worked.
Right.
And I'm not exactly sure when Apple came knocking, but it was after I had left.
Yeah.
So it was sometime between August
Right.
1990 and November when the company was set up in a barn in Swaffham Bulbeck.
Yeah. We can ask about that later.
We could. There are people here who know, probably.
Exactly. One of the reasons Apple did come knocking, though, was because the ARM chips were being used in their products. And that was one of the characteristics of the ARM was its power consumption. Now, I remember sitting in the White Swan with Mike at some point around this time and him drawing on a piece of paper and showing me the ARM chips MIPS per watt and saying, this is why it's going to work. This is the most important thing about it, and nobody's realised this yet. This is the real secret to why it's such a brilliant chip. And he was, of course, completely right. You did have a remarkable efficiency in terms of how much processing power you got out of the chip, didn't you?
Yes, and some of that was based on this thesis that I told you earlier, that exploiting memory bandwidth was key. And on the ARM, it's why the ARM took us from 8-bit to 32-bit without stopping off at 16, because with the 32-bit bus you immediately get twice the bandwidth and therefore twice the performance. We also put the 2 or 3 gates I'm probably most proud of in my life onto the ARM that allowed us to use this commodity memory in a very efficient, fast mode. We could access an internal mode of the memory that doubled its performance at almost no cost. And so we got 50% more overall performance from the chip as a result of these little tweaks. But its low power was partly intentional and partly accidental.
What was the intentional?
Well, we had to get the chip in a plastic package, okay? Because the alternative was a ceramic package which would have added $20 to the price of a chip.
Okay.
And to get it in a plastic package, you had to keep the power below a watt, okay? Because that was the thermal limit of the plastic packages at that time. And the tools we had were not very good at predicting power. And so we applied Victorian engineering principles to make sure we came in under a watt. And actually, we came.
You built it out of iron. No?
It actually came in under 1/10 of a watt.
Right.
So we were an order of magnitude on the conservative side.
Right.
And of course, one of the anecdotes from that time is the first time we tried to measure the power of the processor. You know, I'd reconfigured the power supply to a test board, put an ammeter in, powered the board up, loaded some code, ran it. It was running code perfectly. Looked at the ammeter, it said 0 amps. I thought, well, okay, it's low power, but it's not that low power. And actually, I'd failed to connect the power.
Okay, so it was just
But
running
it-
on magic.
But it was running programs, okay,
Yes.
and a little bit of thought. Other chips on the board were powered, signals going into the chip have protection diodes, and so as long as one of the inputs is at a 1, you get some power leaking in through the protection diodes, and this was enough for the processor to compute on. We didn't test exhaustively whether 1 was enough or whether
You needed a
we
couple
got lucky, but that was.
Okay,
was-
so we're talking about very, very low power.
Yes, it was extremely power efficient by the standards of the day.
Right. The power consumption sort of matters to you today, doesn't it? Because you're putting 1 million ARM chips. I think you're up to 500,000.
I have 500,000 at the
You have
moment.
500,000 in a single configuration.
Yes.
And so presumably that project should be quite low power too. Tell us about what you're doing with 500,000 ARM chips.
Well, for the last decade or two, I've been sort of focusing on designing silicon to support real-time brain models. Okay, so we're building computers that have a connectivity.
So we're just going to run
Inspired.
that one back again. because you might possibly have just included 2,000 years of Western philosophy as a sort of an aside here. So you're designing silicon to support real-time brain models.
Yes.
Okay, modeling the brain in real time in silicon. Okay, we'll go with that. How?
So we've architected a machine that has a particular communications structure that allows it to support things that work in a similar way to the brain in real time. Okay, now the brain is based on just under 100 billion neurons with 10 to the 15 connections between them, and your entire personality, the fact that you're different from me is defined by how those 10 to the 15 connections are formed.
Yep.
Firstly, through your genes and then through all your life experiences. And so we're all defined pretty much by those connections. The neurons communicate primarily by emitting pure impulses to each other. They go ping every so often. And the nature of the way those pings propagate means that the only information is in the timing of the ping, not in the size or anything. Because,
Okay.
and so the challenge in Spinnaker, which is this big machine, is to model the degree and style of connectivity that you find in the brain.
Right.
And we've done that by mapping each of those pings into a little packet, and we connect things through a packet switch network, which is like the internet, only very much scaled down.
Right.
And we can communicate vast numbers of pings. Now, just in case you're getting worried about the idea of brain modeling, with 1 million ARM cores, we can only get to about 1% of the scale of the human brain, and that's using quite abstract models. So we've simplified the biology a lot, and we're still only at 1% of the scale of the human brain, or as I prefer to think of it, 10-hole mice.
Right, or one Remain voter, one Leave voter rather.
I thought you said we weren't going to get back to that topic.
It was too good an opportunity to miss. It was, of course, an entirely agnostic
I
joke.
thought they were lemmings, not mice.
Ah, very good, very good. So 10-hole, but you can model 10-hole mice. There are a number of questions around the project. So firstly, did Spinnaker start from a long-term desire to investigate how the brain works that you'd nurtured over the years, or was it something that became possible as you saw how the speed of our processors, the power of the systems was developing? In other words, where did the desire to do this come from for you individually?
So I'd been in conventional processor design for 20 years, towards the end of the 90s, and I'd seen processors increase in performance by very large factors. And yet there were still things that were difficult, in the 70s, that were still difficult in the 90s. All this compute power just didn't seem to make problems of things such as, recognizing your mother go away. It's possible to write a computer program that will recognize a face now, but it's very hard, unreasonably hard.
Right.
Whereas, human babies will do it within a few weeks of seeing a face, they'll be recognizing them.
Yes.
So I got a bit sort of intrigued in the difference between the kinds of information processing that happen in machines and the kinds of information processing that happen in brains.
Right.
And the first you know, I'm an academic, so I have to get funding to do anything. And in '98, I think because I was getting support from ARM for some of the IP we've been developing with our asynchronous ARM processors, I was given the opportunity to bid for what was then called a Realizing Our Potential Award grant from EPSRC, which was a grant that you could bid for if you had some industrial money. So ARM was instrumental in this at that stage. But one of the requirements was you had to do something different. So you couldn't use this grant to continue your previous line of research. You had to branch out.
Right.
And the title of the grant, if I remember it right, was Efficient VLSI Implementations of Inexact Associative Memories. Okay? So that was the first little step in this direction. And an associative memory is one that sort of recognizes things you feed it and gives you things it's connected with.
Yeah.
And I'd always liked associative memories. We managed to get some in the ARM3 cache in the late 80s.
Right.
And I'd used them for a number of things in the meantime. But as we studied ways of, the characteristic of a standard associative memory is it's very brittle, like most computing stuff actually.
Yeah.
That if you give it the right inputs, it gives you the right outputs.
And it's therefore very efficient.
But if you give it slightly incorrect inputs, it gives you garbage.
Right.
Okay?
Yeah.
And that's a characteristic of a lot of computing systems. And so the theme of this project was to try and soften that behavior a bit. So that if you gave it something that was nearly right, it would give you something back that was also nearly right.
Okay.
For some value of the word nearly.
It's some useful value of the word
Yes.
nearly. So it sounds like what you're doing there is building up from the capacities of the silicon into something which bears a passing resemblance to how human memory might work.
Yes.
It's not an attempt to build a memory.
No. But the corollary of this piece of work, which took, I think it was a 3-year grant, the corollary was every way you looked at softening associative memories, you ended up reinventing neural networks.
Right.
Okay. And so at the end of this, I kind of threw in the towel and said, well, if that's the conclusion, maybe I should look at neural networks properly.
Okay.
And then I started a path of studying how computational neuroscientists build models of parts of brain, which they've been doing for years.
Yeah.
And what kind of machine might offer improved support for those models than a conventional computer.
Right. And this is where your personal history comes to bear, because you are a chip designer, because of your 20 years of experience, you could presumably see opportunities to model in hardware that the software-based, the computational scientists would not have noticed or been aware of.
Yes, that's right. I tend to think in terms of what's possible on hardware and how does it provide a sort of support for a particular class of problem in a new and improved way.
Right. And there's one overarching principle that you bring to bear in that, isn't it? And that's the idea of simplicity. How do I simplify this down to something?
Yes. Well, and on Spinnaker, this was very necessary because the center of each Spinnaker chip is a packet router. Okay. Now, a packet router, there's probably one in this building, is typically a 19-inch rack box about that high, that wide, that deep, and consumes 50, 100 watts of
lots
power.
of flashing lights on the front.
Lots of flashing lights on the front. And basically we had to take that and put it on Spinnaker in about 4 square millimeters of silicon and with a power budget below 100 milliwatts.
Okay, that's
Right.
a challenge.
Yeah, so that's what we did. And in fact, the evolution of the Spinnaker architecture, the one thing that's remained constant is how we do that, and that's the key innovation in the machine.
Right. And so let me ask you about that. Does that resemble in any way how a biological system works?
No.
Okay.
No, the point is that the biological system implements its connections by having individual wires for each connection.
Yeah.
So each of your 100 billion neurons effectively has a thing very akin to a wire. It's not purely electrical, it's electrochemical in the way it operates, but it sends an electrical impulse.
Yeah.
And each neuron has an individual wire that goes to 10,000 targets typically,
Yeah.
maybe more. Now, you can't do it, you can't build the electronic model with physical wires in the same way because you can't make enough wires. And so, but you exploit the fact that the biological signal is quite slow. The signals in your head move at about a few meters a second. you exploit that to send many signals down a smaller number of wires.
Okay.
So basically you give each neuron a number, and in Spinnaker it's a 32-bit number, so we can model up to 4 billion.
Okay.
And you propagate that number, it's a 32-bit number, it goes down a small number of wires depending on how you encode it. And
Yeah.
then when it gets to where it needs to go, which is the routing trick,
Yeah.
it's then recognized as being neuron 352 because the packet contains number 352.
Okay, and then neuron 352 can do the thing it is programmed to do.
Yeah.
How then do you start telling those neurons where to start from? I presume you're not coding this in C, you're not writing programs, but there must be a way of setting an initial state which can then start to learn. What's the mechanism for working with Spinnaker?
So the high-level user interface for computational neuroscientists is a neural network description language, of which there are a number because people have been computing networks for a long time. A popular one in Europe, if that still exists, is Pine, which just stands for Python Neural Networks. So
Right.
and Pine allows you to write lines of Python with things that describe populations and things that describe projections. And then we have a stack of tools which take the Pine description and map the problem onto as many processors in the machine as is appropriate for the problem.
Right.
And construct all these routing tables to connect these neurons together with appropriate graphs.
And we can go out and do that, can't we? Spinnaker's
can, if
out
you-
there on the open web.
If you join the Human Brain Project community, which again is a European project, flagship project, at least it was until it still is. If you join the HBP community, then you can submit jobs online from anywhere to Spinnaker.
Right.
And it's very easy to do. And one of the things I've been doing for the last few months, which I've still got to finish off properly, but I've built a network which solves hard Sudoku problems
Oh, really?
in about 5 seconds. Yes. And it's entirely based on spiking neurons. It's a stochastic network, so the spikes are carrying information about probability distributions.
Yeah.
It uses 13.5 million synapses, I think, or something.
Right. Okay, so this is our takeaway from this evening. We can all go and start doing this ourselves because it's important that you get your system used because, of course, you still don't know yet whether it works properly, whether it's the right approach, do you? This is leading edge research into a hard problem to see whether it is actually an answer.
The fundamental scientific challenge is understanding how information is processed in the brain, and it's still a great mystery to science. When you think about scientific frontiers, you typically think about incredibly small, large hadron colliders or incredibly large square kilometer arrays. But we all have this thing inside our heads, which is about 2 handfuls of stuff,
Yeah.
and we have no idea how it works. We know lots about the low-level details, some about the top level, but nothing about the intermediate levels. And the only tools we have, the only instruments, are computer models.
Right.
Now, we've adopted a particular approach to modeling. We aren't the only people playing this game. In the HBP, there's a group at Heidelberg that has some very advanced silica models, and they run 10 to the 4 times faster than biology. And there are pros and cons of being fast. In the US, IBM has moved into neuromorphic hardware with their True North chip, which is a very aggressive piece of silicon that's really sort of more suited for applications than for research.
Right.
And there are others.
Okay. Well, we'll have to see over the next few years how Spinnaker works. There's a thread throughout your working life of taking these hard problems, of stripping away the complication and then finding something that can be implemented. And I remember when we were talking in advance this evening, you said it's often very difficult for people to know how to measure simplification.
Yes.
Because if your job every day is taking stuff away, then you're not actually being very productive.
Yes.
And
This is a particular issue that came up with I think Acorn had a new technical director that came in who brought in industry measures of, a chip designer should design this many thousand gates per month, and that's, productivity. And I said, well, if I have somebody take a design and remove 5,000 gates from it, I think that's very productive, but on this measure it's negative. My observation of the computer industry is that a lot of people basically earn their living by making something a bit better, by making it more complicated.
right.
And I like to think most of my life I've spent doing the opposite. making things simpler and more efficient through that route.
I'd say having observed what you've achieved and having seen the various honours and fellowships that you've achieved throughout that, it's clear that your peers feel the same way. So there are those who appreciate the work you've done to make it possible for us to begin to model the brain and then the mind. And I say I do just look forward myself with Spinnaker, which I find one of the most exciting research projects out there, to see what happens next as it goes into more, is more used more heavily.
Yes, we spent 10 years building this machine, which is now sitting there. It's now functional. People are beginning to use it. But of course, we have about 70 published papers on how you build a machine like this.
Yes.
But the real test is what kind of science it will deliver. And we've just started on we've just got the machine. It's been online since the beginning of April. So
tomorrow you can all go out and build things on Spinnaker. For now, we've got a few minutes to take questions or corrections from the audience. If you're going to put him right about something, please say in advance, okay? Would anybody like to make any comments, make any points, or to ask Steve some questions while we've got him sitting here? Yes, someone at the back who I can't see
Alex.
properly. Oh, Alex, sorry.
Hi Steve, thanks for your talk. One of the challenges in computing about making things simpler is often that one trades off the use of software for the use of hardware. One tries to, broadly speaking, move things closer to the metal to enable them to go faster or be more efficient. But there's obviously a limit to that. And Spinnaker chooses not to do that. Spinnaker is a programmable machine. You haven't tried to build a dedicated chip that carries out the work. You've left an arm in the middle and written programs that run the arm. So I'm just interested whether you care to say anything about, do you think it would be worthwhile to try and go any further towards the hardware? Do you think you'll eventually be able to do that? Or does that lose too much flexibility? And is that actually missing the point?
Well, I think you've raised precisely the issue there of flexibility versus efficiency. And the design of Spinnaker went through a number of cycles while I was thinking about it sort of in the early part of this century. And I had this idea that you could cast neural algorithms into hardware and so on. But when I looked more closely, my observation was that the computational neuroscientists, there's no consensus on what the right algorithms are. There are many different models of a neuron, simple ones, more complicated ones, very complicated ones. Even at the level of the synapse, which is actually where most of the compute cycles go, the issue of what is the right learning rule, and is there a single right learning rule, or do all synapses which display plasticity do it in the same way, is completely open. Okay? And so if you put these algorithms into hardware, you've basically made a design decision that may or may not be right. Now, IBM has done that. Okay, so in IBM, their neural model's got a lot of parameters, but basically they've decided this is the right model, and they've decided in their synaptic structure, they've decided this is the right way to do a synapse. And their synapse is a single bit with a global modulator, which means they can't do any learning on true north. Okay, now learning, to me, is central to what biological nervous systems are doing. But as I say, you can train a network in a computer, in a software model of the chip, and then you can download the trained network onto true north. And that's why I think it's very efficient as a delivery platform. But if your goal is to support research as broadly as you can, then I think keeping the issue of the neural model and the synapse plasticity rule as software gives you the maximum flexibility. So I see Spinnaker really as a research platform. When the answers emerge to what's the right model and what's the right learning rule, then you can go and re-implement more efficiently. But we don't know at the moment. And so I think flexibility is still of the essence as we explore this space. But I do see Spinnaker primarily as a research platform, not as a delivery platform, although there are some people who see it as a delivery platform. And so the one thing we did cast into hardware in Spinnaker is this communications infrastructure, and that is the key thing. Spinnaker can do things, on a machine that will have cost order of £1 million to build, plus quite a lot of labour, that you cannot do on the new Chinese 100 petaflop supercomputer because the communication on HPC cannot support this kind of real-time communication on very tiny packets. I mean, Spinnaker carries a very large number of very tiny packets. Big supercomputers carry lots more data, but they do it in big chunks.
Thank you. Thanks. Any more questions or comments? Would anybody like to?
Can I just ask, I mean, you've got Moore's Law, doubling the number of...
Not say who you are, David.
David, ex-BBC. How does Moore's Law come into your, I mean, in 10 years' time, when you have, you know, you say you've got 10% of the brain modeled in a sense, but you have the rest of it modeled. I mean, how is it going to expand in the future?
Well, Moore's Law is slowing, okay? I mean, it had to slow sometime, and it's now tangibly slowing because we are approaching atomic limits and designing. There are many parameters by which you can judge this, but the cost of designing a chip has been growing almost uncontrollably, and the cost of building a factory to make them is also growing uncontrollably. I mean, we're not at hard physical limits. It doesn't suddenly stop, but what happens is all the costs associated with keeping it going become uncontrollable, and the cost per function, which is the thing that's driven the chip business, driven Moore's Law at its doubling every 18 months rate, that stopped. Okay, so the cost per function is no longer going down as you shrink. You can still shrink, it doesn't get better. Spinnaker's old technology. It's 130 nanometer technology, so it's 10 years at least out of date, and yet the machine is competitive. Partly because we don't have a lot of industry competitors in this space. Okay, but interestingly, it's been observed that the Heidelberg project, the Spinnaker project, and the True North project at IBM have all taken 10 years from concept to delivery. So we're not that slow. Partly, of course, this is because the IBM project wasn't a big commercial project with the full business resources. It was, you know, funded from DARPA research projects, so living off the fairly sort of thin energy supply that we live off in academic research.
Okay.
But I mean, we are within the Human Brain Project. We are doing a technology step. We're going to a more expensive, more up-to-date technology, which will give us about one order of magnitude. But where the second order of magnitude will come from is not clear at the moment.
Okay. There was, in typical BBC producer style, David put his hand up and then started speaking immediately. There was another question behind him.
I'm going to fit a bonus question in. What node are you moving to next?
28 nanometer.
I was hoping you might say something about ULAs, about that thing before you did VR,
Yeah, so our first exposure to chip design was the ULAs that we put on the BBC Micro.
ULAs are?
Uncommitted logic arrays.
Thank you.
These are chips which have a whole lot of gates on, but how they're wired together is designed by a final single-stage process, which means designing them for a particular function is much cheaper than designing the whole chip from scratch. And the ULAs we started with on the BBC Micro were built by Ferrantes in Oldham in North Manchester. And there were two, the VidProc and the SIRProc, for video processing and serial processing. And they each mopped up 10 to 20 chips, so they reduced the chip count. I mean, the BBC Micro had 102 chips on the circuit board. It was a ferocious number, really. But it was reduced by a few tens by these ULAs. And they provided us with hours of entertainment.
Yes.
We had real trouble with the video processor running it at full clock rate, and we struggled to get that to yield.
Okay, thank you. Well, from uncommitted logic to a committed academic exploring the limits of human consciousness, I'd like to thank Steve for joining us this evening, sharing his time with us, and now ask Mike to close proceedings.
Well, I'd just like us to thank these two for having entertained us and to say there is plenty more food and drink outside, and if you are feeling like indulging in a little nostalgia, if you go right to the back on the right hand side, you'll see our recreation of the 1970s office, which may bring back some memories for some of you. So thank you for these two.
Trigger warning. Thank you, Steve. We're done. finished now. Off you go. I think some people need a trigger warning about going into the 70s office, though.